Alrighty, welcome back. This is a nuclear test. This is an earthquake. They look distinctively different. By the way, there are now smart apps, or apps for the smartphone, and they could be smart apps too, that for your iPhone or Android can actually detect earthquake waves and then export that data. They're not super accurate, but it's kind of cool. And it's free. Okay. What happens if your seismograph station is near the focus? Well, here are the P and the S waves going through the crust. Even though they have a little bit further to go, they move faster. The P wave arrives first, the S wave arrives second, and then the surface wave, which goes right along here, really slowly, arrives third. If your station is further, the same thing happens, but it takes longer for the P wave to arrive. The distance or the difference between the arrival of the P and the S wave is greater. It makes sense. Let's say you had a friend that was walking 2 feet a second and you walked 1 foot a second. After 10 seconds, you'd be about 10 feet apart. After 100 seconds, you'd be 100 feet apart. So the bigger the lag time in here, that means the further away the focus of the earthquake was. Again, P and S waves start out at the same time, but P waves get farther and farther ahead with each passing mile or kilometer. Now we can use all the information for this kind of thing to make what are called time travel curves. They make it fairly easy to identify where earthquakes occur. Let's say you're in Denver, and going back to your seismograph, you figure out that the earthquake occurred about 2,000 kilometers away. All you have to do is draw a circle, and you know the earthquake was 2,000 miles away. So you get one of your freshman students and you say, hey, go out there 2,000 kilometers and walk around in a circle and let me know when you get to the earthquake zone, okay? And if you get into the ocean, here's an inner tube, you're going to have to swim. Okay, it's not a good idea. So you then take your little station at Lima, Peru, and they find out that it's 9,000 miles away. So the earthquake has to be both on the green line and on the blue line. Well, it has to be either there or there. So with 2 stations, you can narrow it down to 2 points. Then take your St. John station, but that's not Nova Scotia. At any rate, St. John station, they figure out it's 5,300 kilometers away. They draw a circle, and the only place where all 3 of those circles triangulate, 3 circles triangulate across, is right up here near Vancouver, it looks like. This is called triangulation, and this is how you figure out the epicenter of an earthquake. Here's a better view of it. Excuse me. Now, here is what we do with that then. We use a time travel graph. We figure out the distance between the P and the S arrival times, a 3-minute interval, for example. We go up here until we can see a 3-minute interval, and then we know how many miles away it is. It's not that hard. My explanation is not good. Okay, the shadow zone. If there's an earthquake over here, the P waves in blue tend to get curved as they go down into denser and denser crust. They don't travel in a straight line. In the same way that water that goes into a pool gets bent. You ever stick your pool sweeping device down in the water and notice how it gets bent? Same thing happens to waves from earthquakes, seismic waves, as they go down in the ground. Now, as the seismic waves go through the mantle and hit the outer core, P waves really get bent. Then as they come back out and go into the mantle again, they get bent again. So what happens is the P wave coming right here and just missing the outer core goes right there. The P wave right next to it, which just barely hits the outer core, ends up getting moved. And there's an entire area here and all around the globe that would be like a basketball sitting on a donut, which is called the shadow zone. This is one of the ways that we know the outer core is liquid. Something else that's cool, anywhere opposite the earthquake, you don't get the S waves. So if you do your geometry, you can figure out that whatever was between this point and here has to be liquid. We have seismograph stations all over the planet. I accidentally ended up on this one in the hardened sand dunes in southern Utah once. It's run by Lawrence Livermore Laboratory. And then, 20 years later, I ended up working for Los Alamos National Laboratory in this kind of stuff. Now, depth of earthquakes. Most earthquakes occur fairly shallow, 0 to 70 kilometers. What is that? 42 miles. Intermediate earthquakes from 42 miles up to, oh man, got to do the math, 60, 60, 180, about 210 miles approximately. Deep focus earthquakes, just a few of those. Why don't we get earthquakes deeper than that? Well, the problem is that after earthquakes go deeper than that, this becomes too fluid. There's no tension built up because this stuff flows. You can't crack liquid water. You can crack ice. The crust is more like ice. Stuff underneath, not the same way. Now, how do we measure the size of earthquakes? One way, magnitude, the Richter scale, which goes from 1 to some number. We don't know. As big as we want. There's a way to measure intensity, and this is completely subjective. It is in Roman numerals, and it really does go from I to XII. And there's a better thing called moment magnitude, which your book does not talk about too much. It compares the rock strength, the surface area of the fault, and the amount of movement. Let's look at the Mercalli scale. Again, this is very subjective, but it can tell people how much damage is done. It goes from not being felt at all to felt by all. Many people run outdoors, and people really do this. They behave similarly in earthquakes. Some heavy furniture is moved, a few instances of falling plaster. Let's go up to 10. Well-built wooden structure destroyed. Wood can flex. Masonry doesn't flex, so most masonry and frame structures destroyed with foundations. Ground badly cracked. Rails are bent. Does that really happen? Yeah, I'll show you in a while. Considerable landslides, and all the way up to 12, damage total. Waves seen on the ground, lines of sight and waves distorted, objects are thrown upwards into the air. Now, a long time ago, there was an earthquake in Charleston, and this is the Mercalli reading from it. Got up to 10 right near Charleston, 9 next to that, 8, and you can see decreasing damage. What's interesting is bells were rung all the way up in Boston in the steeples. Now, here is a comparison, but it's not exactly accurate. If you have a X to XII on the Mercalli scale, that's going to be 8.0 on the Richter scale. A lot of damage. Only 1 or 2 of those occurred in a year. Very minor earthquake, I, or 1, Roman numeral 1, on the Mercalli scale. Richter magnitude is about 2. About 600,000 of those a year. Now, I did have a student once in college who said, hey, every time my ears ring, I go to check the web and see if there's an earthquake. It's true, there's an earthquake. It must be that my ears can hear earthquakes. What do you think? Was she right? Because every time she checked, there had been an earthquake. Well, yeah, but that's kind of like dowsing and finding water under the ground. There are 600,000 earthquakes a year. About any time you check, you can find an earthquake within about 2 minutes of your ears ringing. It's kind of a silly thing to say. Now, here's an important thing about the Richter scale. From 1 to 2 is a certain amount. From 2 to 3 isn't the same amount. It's bigger. 3 to 4, 4 to 5. You get the idea. In fact, this is called a logarithmic scale. An 8 is way bigger than a 7. So in the case of the recent Japan earthquake that was 9 point something, I have to make my little cursor go way off the top of this graph. Here is a nice little graphic. Here is the largest earthquake recorded, at least in my lifetime, down in Chile in 1960. It was a 9 point something. The Japan earthquake was right in here. Here's the equivalent energy in exploding TNT. Here's the description. Then here's how they compare with volcanic eruptions. Earthquakes can be a lot bigger. By the way, notice that the energy in different things is over here. The Hiroshima atomic bomb, your average tornado, lightning bolt, Oklahoma City bombing, the World Trade Center collapse, and here's a moderate lightning bolt. Now again, these are where earthquakes tend to occur in the United States. Take a look at Arizona. We're pretty safe. We've got some up by the Grand Canyon, and it looks a little iffy with all this red, but these are really small quakes, not big ones like over here along the plate edge. And Hawaii, it also gets earthquakes. Why? Volcanoes, large amounts of moving molten stuff under the water. Now again, what kills people in earthquakes? Well, ugly trucks, but also fires and disease. Now again, when you get down in the earth, things become ductile. They don't break. So earthquakes tend to be shallower rather than deeper. And this is going to get a little bit repetitive. Here are the effects of earthquakes. You get ground motion, buildings being toppled. You get fire that you can't put out because your water lines are broken. You get landslides, and those landslides can cause big tsunamis. I'll share that with you. Liquefaction, that was in one of the movies, or is going to be in one of the movies that you're going to see, where the water that's down in the ground gets compressed and brought up to the surface. You get little mud volcanoes. It's kind of cool. Permanent displacement of the land surface, and one of the biggest killers in earthquakes, I know it's weird, is a tsunami. People drown in earthquakes. The most deadly earthquakes in history? Oh, you know what? I didn't put the 2010 one in here. I need to add it in because I think that was well over 200,000 people. Tangshan, China. This is an underestimation. Numbers have gone as high as 600,000, but China back in the days didn't want to talk about losing people because their form of government would not allow people to die. So these numbers are iffy, but in one earthquake, at least 250,000 people died. This was on land. Sumatra, Indonesia, $230,000. Wait, $230,000. 230,000 lives. Was that the one? The Christmas Day one? That was. My bad. It is in here. Italy, 1908. This was a lot of people for back then. 100,000. Let's see any in the United States. Guess what? We are fairly safe. We keep going down, down. Even the big earthquake from Japan. Not in here. The Tohoku earthquake tsunami that destroyed the nuclear power plant. It doesn't even make it in this top list. In the United States, 3,000 from earthquake and fire. Our next biggest one, 165, 128, 115. Again, the earth doesn't open up. You fall in, then it chews you like a dog chewing on your arm. Yeah, the earthquake can move back and forth a little, but it doesn't do that kind of thing. You do get scarps forming where the land will drop and then guys holding sticks. Okay, this is to measure how high the drop was. And you do get water being squished to the surface, the knife there for size comparison, and making little mud volcanoes. And you do get the collapse of unreinforced masonry structures. I was in Egypt a few years ago, traveling from Cairo south toward Thebes, or the Aswan area. And there were these tall buildings that were just stacked bricks. And I thought, man, if there's ever an earthquake there, it's going to be bad. Guess what? A few years later, there was an earthquake there. And I don't know if it's in here, but lots of people died. I don't know how many thousands. We will pause here and be right back.